Okay, how was it that we wrote the speed function? I've got acceleration, and I need to write these speed functions so that so that we were able to graph them. How did I do that?
You took the integrals of, I mean, the antiderivative of both
Did we
functions.
take antiderivatives?
Like, you take the integral of uh, the two functions, which would result in an antiderivative.
Well, so antiderivative is more refers to like an algebraic process, which we haven't really done yet. So yes, so we're doing integral net accumulation functions. And a derivative then would be like, which we're going to do soon, it's like how we get a closed form of an accumulation function. So we haven't really done that yet, but you are correct. We're doing integral, say from a to t of what? So if we want the speed of or the velocity of car one, it's going to be the integral of a to t of
a2 of t.
a2.
Yeah.
So
What,
we need the rate of change of car one, right? So if
sorry, a1.
Yeah. Okay, and so that's what we did. We set up these net accumulation functions of what is net accumulation of changes in velocity. And so then as those changes in velocity accumulate, we track this as a velocity function. So we did that for both of those. And we found that indeed the speed of car one was faster until we got to this point right here. And is this where car two now passes car one?
So no, it's when their velocities are equal.
Right. So which car is ahead here?
Whichever one the blue one is.
Yeah, car one. Okay, so car one. Yeah, so car one is still way ahead. Its velocity is higher for this whole time, so it's increasing its lead in terms of distance from the start line, right, or displacement. So, but at this point is when cars 2 speed finally catches up to car 1. Okay, so what about distance now? So suppose I'm interested in, I want to know, so what's happening here now? Car 2 is going faster than car 1. So does car 2 in this time frame ever catch up to car 1? So will car 2 pass car 1? Let's see, in the first, I think I've got it to 8 seconds. Let's see. Yeah, 8 seconds. So in this 8-second period, at the end of the 8 seconds, will car 2 catch up and pass car 1? What do we think? Yes or no?
Yeah.
Okay, I have a vote for yes.
No, I don't think it will.
Okay, we have a vote for no. Okay, so how can we know for sure? So we want to know for sure with given these velocity functions, will car 2 pass car 1 or not by 8 seconds? How can we know for sure?
Could we take the integral of the difference between the velocity functions?
Okay, so let's keep the cars separate. So how can we do that, keeping the cars separate?
Could we graph the position function to the integral of the acceleration?
Yeah, good. So this question of has car 2 passed car 1 is a question of distance now. So we want to write distance accumulation functions. We'll use S because estimate arc length. It can also mean distance. So it's kind of the same thing. But don't confuse that for. So let's actually use D. Let's use D because I don't want to confuse. That we're not gonna be measuring the arc length of this velocity function, right? It's not the arc length of this, which is the distance the car traveled. So let's not use S. Let's use D. So if I want to write a distance accumulation function, what do I need?
Speed and time.
Okay, so rate of change of distance, right? And that rate of change of distance, that's changing itself. So we're going to need net accumulation, right? Net accumulation at the rate of change of distance. And so that rate of change is our speed function. So we're going to have d1 equals so this is going to be the form of our distance accumulation functions. Because speed is the rate of change of distance, we're going to have the net accumulation from a to t of the speed of car 1. And that's going to be our distance. So I have that kind of set up here in a different file. Where is it? I guess I put it down here. I thought I had it already, but let's see. Displacement right here. It is. Okay. So, and I did call it S, and so yeah, let's put those in. So the distance traveled by car 1 is going to be the integral from a to t. And just so you know, this is not arc length of some curve that we're showing here. This is just another name for the distance that the car has traveled. So it's not arc length of any graph. Just so you know, in this context, it's not arc length. Okay, and so we want v. And so now my v function is just looking for a single variable. So I'm going to du. Okay, so how does that look? So if you see a mistake, you can let me know. And so this one will be v2. Okay, how do the displacement functions look here? Okay, so now I want to graph those displacement functions. Okay, and so I'm going to graph, so on the vertical axis, I'm going to put the displacement starting at time 0 and then on the x-axis, I'm going to put the time elapsed. Okay, and I want you to see what happens here. So I'm going to hit graph, and I want you to watch what happens, right? Here we go, watch. So what's happening? Why is this taking so long? I thought technology is speedy for us, right? Technology can just give us, compute things and plot graphs very quickly, but here it's telling us graphing, go get some coffee, okay? You got a minute here. So what's going on?
It's because the functions are in open form.
Okay, so, but we've graphed lots of open form functions before and it didn't take this long. So yeah, you're onto it, but why is it taking this long?
Because the distance function is open form and the acceleration function is also open form.
Right.
So it's double the open form.
Yeah, excellent, good job. So this, what? So we're graphing the distance function, which is open form, but that's based on our rate functions, our velocity function, what? That's also open form, right? So for every distance, it's accumulating those changes in distance, and every time, for every one of those little accumulated changes in distance, it has to accumulate all the changes in speed. Every single time it does an accumulated change in distance, it has to, from 0, have to calculate all those changes in speed to get that. So you got this 2 layers of open form. 2 layers of open form. And so this reiterates the point that open form is not, it doesn't compute things easily, even for even for technology, when you double it up, when you double up open form, I mean, that took like over a minute for it to graph that. Okay, so really important point there. Open form, it shows us the process, it shows us the meanings of the values it computes, but even so, we can even give technology a hard time with it, right? So it really took a long time to do that. So are these distance functions doing what we expected? Blue was car 1, and so what did we say? The speed of car 1 was faster at the beginning, and so it's getting a lead here. It's getting a lead, but then starting around here about 5.6 seconds, now car 2 is faster after that, and so it starts to catch up. So the question is, did car 2 pass car 1? And so I've not revealed that yet because I'm still not showing 8 seconds here. So I'm going to keep you in suspense, and I want to show you I have another function here, or another GC file. And with this GC file, I have found the closed forms of the distance functions. And these they look a little complicated, but their bark is worse than their bite. They're not that bad. So we got like a cubic here, and a linear term, and a sine. Okay, so you have a cubic term, a sine function, and a linear term for the first, and then for the second, something similar, a quadratic, and then a cosine, and then a constant. Okay, so here are the two closed forms of those same position functions for this one over here. Okay, now I'm going to graph this. What do you think is going to happen?
It'll be a lot quicker.
Yeah, it's going to be so quick that you got to make sure you don't blink, okay? Make sure you don't blink. So now I'm going to graph these same position functions in closed form. All right, and I'll do it on the count of 3. So make sure you watch. Don't blink. Ready? 1, 2, 3. And there it is, right? I'll do it again. One, two, three, graph. Instantaneous, right? What underscoring the point that closed form, easy to compute values, easy to calculate. Okay, and so then technology can do this, can find all the points and plot all the points almost instantaneously. Okay, so the big reveal. Did car 2 pass car 1? No. By 8 seconds, car 1 is still barely ahead. Car 2 did not, at 8 seconds, didn't pass. Because the y coordinate is the distance traveled, so the y coordinate of the car 1 is greater than. I can get onto the other curve here. Down here. At 8 seconds, the y-coordinate of car 1, the blue graph, is greater than the y-coordinate of car 2, the red graph. So a valiant effort from car 2, but it did not catch up in those 8 seconds to car 1. All right, questions on this? Questions on...
Are we gonna have like GC practicing problem solving questions?
Mm-hmm. Yep.
Do so.
Definitely.
Thank you.
Yeah, definitely. All right, so that was our little kind of mini unit on acceleration and velocity and distance. Any final questions? And then, as we talked about before, so someone brought up antiderivative. So we're getting close to the time when we're going to start learning how to find a closed form. So this is the closed form of the distance function as opposed to the open form, right? Open form, which was actually like double open form. Our rate of change was an open form. And so we're coming up to a point in the course where, given that open form, can we do some algebraic processes to write closed form. So that's coming soon. But for now, we want to focus on writing those accumulation functions in open form like we've been doing all along, and let GC graph it for us or find values of the quantity for us using function notation. Okay? All right, so let's move on to work. We're going to do work. Did you know that we haven't done work yet in this course? Get it? I got jokes. So work is a physical quantity. And it's the force applied over a distance. Force applied over a distance. And so it's quantified as force times distance. Force times distance is kind of the very most kind of core calculation that gets you amount of work. Okay, so force applied over distance, multiply that force times the distance, you get the amount of work that was done to move an object, right? So it's like moving an object. Okay, the unit of work is newtons, that's not minus, times meters, so Newton meters, which is joules. So Newton meters, right? Force is in newtons, distance in meters, multiply, Newton meters is joules. Okay, so work, like we talked about, like I said, is dependent on moving an object through a distance. Okay, so this young man here at the Midvale School for the Gifted is pushing with a lot of force, as much force as he can. Okay, how much work is he doing? It doesn't matter how hard he pushes. He can push with 1,000 pounds, 10,000 pounds of force. If there's no displacement on an object, if there's no motion, there's no movement across a distance, the work is still zero. Okay, so he's doing 0 joules of work. Okay, so
if there's like an opposing force, or does that not matter because it's only displacement?
It's only displacement, right? So there is, yes. So if everything's still and you apply a big force and then nothing moves, then yes, there is an opposing force pushing back, but that still the work is 0 because work depends on moving it.
So we don't even worry about that for this.
Worry about what?
Like the opposing force.
Right.
Or,
right. Yep.
Yeah.
So it's when the work results in a displacement of the object or a distance that the object moves. And so as you push an object, what happens to the distance or the displacement of it? So when you first start pushing, how much work has been done? The moment you start pushing, how much work has been accomplished?
No.
None if there's no displacement.
Right. It's right at the beginning, there's no work yet. So what happens? Now the box, let's say we're pushing a box. Now the box starts to move. What happens to the displacement as you do that? The displacement, what, increases? And so then what happens to the work?
It increases proportional to the distance.
Yeah, right. So at distance 1, you have some amount of work, and then you push a little further, and your work is it's increasing, right? So we really think about this as it's the accomplished work over a distance, right? So by the time we get to D2 here, we've done work all along the way. That work has increased, bit by bit as we've pushed the box from here to D2. So what does that remind you of? So you said there's no work here, and then the work is, as distance increases, the work is going to increase. And so you're accomplishing work little by little. And so what is that principle? Accumulation, right? So this is the perfect chance to apply accumulation. As you continue to push, the work accumulates. The amount of work accumulates because your distance is increasing. But then there's other complications too to this. So maybe the force being used is varying. Maybe there's a force function. That's going to complicate matters. And then maybe the distance varies in odd ways. Maybe it's not a straight distance. Maybe there's going to be turns and it's not going straight. So both of these things complicate this this endeavor that we have of trying to find a work function, right? The accumulated work since the force started being applied. Okay, so let's look at this example about the pushy ant. And so an ant pushes a seed along the path shown. And the ant pushes with a constant force of 0.03 newtons. That's nice, right? That's a nice, simple way to start. But, so we have constant force, but we have this wavy path, right? So you're looking down on the path of the ant. So this is bird's eye view, looking down on the ground. And the ant is pushing something along this path. Okay, so let's talk about that. So because this path is a weird shape, so let's talk about, say, right here. What do we have to do? We're going to look at little amounts of work, right? So little amounts of work. So how would we calculate, say, right down there at the bottom, how would we calculate a little amount of work that the ant does in pushing the seed?
May I try?
Sure thing.
Would you use arc length at all? Because that would be the raw distance of where the ant is moving.
Okay,
Would that
good.
be applied here at all?
Excellent. It has to do with arc length. So what's our formula for work? Work equals
Force times distance.
force times distance. So how can we apply that to this situation and write how much a little amount of work? What would it be?
Force times arc length.
Good. Force times arc length. So what's our force? Or sorry, force?
0.03.
Right. And what's arc length? So how would we?
ds.
ds. Good. And that's what Navin said too. So what's our force?
0.03.
And then we have ds. And what is ds?
Square root of 1 plus the derivative of the function squared.
Right, so this says this is some function f. This curve represents some function f. So it'd be f prime. Is it only that? Is that ds?
dx.
Times dx. So this whole thing. I don't want to do that. So this whole thing is ds. Let's see if I can do it here. Okay, the square root function times dx is our ds. Okay, so what does this do? So what it does is it kind of like transforms from ds, which we need for amount of work, because the amount of work is going to be according to distance that the ant pushes the seed, and it kind of makes a transformation from that arc length or distance traveled to the variable x, so that we can write the rate of change. So then what is the rate of change of work with respect to x now? So x being what? Horizontal position, like it always is. So this little ds allows us to do a transformation from pushing along the curve, which we need to accurately calculate the work, to having our independent variable be x now, so of horizontal position. So looking at this, if dw equals this thing times dx, what's the rate of change of work? What's the rate of change of work then? I have dw equals what? 0.03 times the square root dx. What's the rate of change?
1 plus f prime squared.
So
0.03 and
yes, remember, dy equals mdx. Now our y quantity is work. So this is our rate of change. 0.03 times the square root of 1 plus f prime of x squared. And what quantity is that? What kind of quantity is that? Is that, you can see it here. The rate of change is?
would that be a closed form?
Oh yeah, everything's closed form here. We don't have any integral expressions. But what quantity is the rate of change of work? If dW equals FdS, then what is the rate of change of work? Just force, right? Force. So this is a force, right? 0.03 is the force. But we just have this kind of a geometric transformation from arc length to x. But rate of change of work in general? Is force. That's an important key point here. So the force is the 0.03, and this is a unitless transformation from s to x. So this whole thing is the force with respect to x, right? So force, the rate of change, force with respect to x, or horizontal position of the ant. Okay, does it make sense? So
Yes.
we're ready to, we've got everything we need to write the work accumulation function, how much work the ant does at every moment as the ant pushes the seed along the path. Okay, we got everything we need. So let's do it. So I've got here's that force function. So let's just graph it and see it. Okay, so I'm going to graph that force function. Y equals f of x. X greater than 0. So just zoom in a little bit. Okay, so that looks like the work the ant has done. Or I'm sorry, that's the path of the ant looking down, like a bird's eye view, looking down on the ant. This is the ground, and the ant is walking like this. Okay, and so now we want to write the work accumulation. So W, we'll call it W sub 1. And we could do a separate line for the rate function, but I think it's simple enough that we'll put the rate function just directly into our expression. And so starting from any value a to x. And so what will be the structure of our work accumulation function? What will be the structure of it?
Integral from a to x.
Integral from a to x, good.
F1 of x.
Okay, good. So the rate of change, what did we say the rate of change was? Yeah, we can use capital F, that's fine. That's 0.03, right? F1 of x.
T.
Need t? Need something different? Okay, are we done? Is that it?
No, you're not
F
done
of
yet.
T.
You need to do ds, but you only have d, but you're expressing in terms of dx.
Right.
I guess is dt here.
Right, so what do I need? I need the square root of
1 plus f prime squared, or f prime of t squared.
I need the derivative f of t with respect to t.
Yeah. Squared.
And then I need dt, right?
Yeah.
Oh, please come back. Oh no. That hurts. Gotta do it again.
Control Z.
I did.
It, GC only lets you do
Yeah,
Control Z once.
I think I made 2 mistakes, so it didn't let me do it. I tried. All right. Okay, now when we graph this, I want you to, while I'm typing, think about what this graph is going to look like. Will it increase? Will it decrease? Will it be straight? Will it be curved? So think about what will the graph look like. Wow, I am flailing here. So you can talk about that while I'm typing. What are some characteristics of the work accumulation graph once we get this put in?
It'll constantly be positive and increasing.
All right, he wants constantly positive and increasing. What about the rest of you? You agree with that?
I have a
Yeah.
question. There was a part of it which was in the negative, so I guess we're doing like signed area in a way. So will it still be increasing because throughout it was increasing?
Right. So
Like
the path goes down here below the x-axis,
yeah.
someplace. So is the work gonna decrease?
No, probably because the rate keeps increasing.
Okay.
No, because the arc length keeps increasing. It's
Yeah.
always positive.
Oh, okay.
Yeah. If arc length keeps increasing, then what about the distance that the ant has traveled? You
It
kidding me?
also increases.
Also increases.
I can't get this now. I've lost the top. Wow.
I didn't even know.
I'm gonna try again. I've got that copied. Yeah, and then what about so it's gonna and at x equals 0, what will the work be?
0 because you haven't accumulated any distance
Okay.
for work to apply on here.
Good. So it'll start at 0. And you said it'll always be increasing. Will it increase as a straight line, or will it vary?
I think it'll be a straight line because you're doing an increasingly small intervals of distance, which is the only thing that could be like changing here because it's a constant force. So I'm thinking straight line.
Okay, so we've got one vote for straight line increasing work, like this. What do the rest of you think?
I don't think it'll be a like directly proportional straight line. I think it will have like little bumps here and there, but like not too noticeable.
Okay.
I would assume.
What is our independent variable for this work accumulation function?
X.
X. So the question is, as x increases, does the amount of work increase constantly, or does the amount of work increase at a changing rate?
Changing rate.
At the beginning, is the work for a change in x, is the work going to increase quickly or slowly?
Quickly.
Quickly, because you see for a change in x here, the ant covers a lot more distance. So through here, the work is going to increase rapidly. And then what about here around 0.5? Or what is that? 0.4, 0.5. For the same change in x here, how about the increase of work there?
There's a varying, like increased rate of change.
That's right. But what about how much work is accomplished around 0.4, 0.5 compared to around 0.1?
There's a lot less.
A lot less, because the distance for a change in x, the distance that the ant is pushing is a lot less than around at the beginning. So does that mean we're going to get a straight line work accumulation?
No.
No, it's going to be wavy, right? It's going to go up all the time, but it's going to be wavy. So 0, comma, x. Do I have my rate function right? So did anyone catch a mistake? Graph this for x greater than 0. And actually, I want to do this on a new window pane here. Let's graph the work in purple. Okay, does everything look good? Let's see if we were correct about our prediction here. So I'm showing from 0 to 1, so I gotta zoom way in here. That's better. That's about right. All right, were we correct with our prediction?
Yeah.
Accumulated work is always increasing. Doesn't matter if the bug is in what quadrant the bug is in, right? Or the ant. And at the beginning, we see a high increase in work, and then later on, say around 0.5, that increase of work is less. Why? Because the ant is covering less distance for those changes in x. All right, so I'm going to pick a point here, and we're going to interpret this point. Maybe? Oh, come on. Why doesn't it let me pick a point? There we go. All right. So, okay, here's the point. 0.559. Is that what that says? 0.559?
Yeah.
And 0.4075 or 0475. Okay, now we got to interpret the meaning of this point. What is the meaning of this point, right? Because this graph is just an infinite, there's a set of many, many, many points, right? A gazillion points. So understanding this graph means understanding what each point means. So what does this point mean? 0.559, 0.0475.
Could we say that at x equals to 0.559, the work done by the ant is 0.04?
Okay. She said that when the ant reaches 0.559, something right around there, for x, the accomplished work so far done by the ant is 0.0475. I forgot what units I was using here. So either joules, so we can say joules. What do we think? Do you agree with that?
Yes, but I'm just confused on like the x point. Like when you say you reach the x point 0.559, what does that mean exactly? Is that the distance when you get to like the distance?
Yeah, is this the distance traveled by the ant?
Okay.
Is it? I'm asking.
No, it is not.
I don't think so.
It's not. And this is the really important point. And a lot of students, that's what they want this to be. They want the distance traveled by the ant to be 0.559. But it's not, because what we said that this was our ds, and the square root is a transformation from distance along the arc to x, right? So this is our function is a function of x, which is horizontal distance. So at this point, has the ant traveled for less or more than 0.559 meters?
More.
We'll say more.
More, according to what?
According to the function f of x.
Yeah, so the ant is moving along the arc like this. And as the ant's moving along the arc, the ant's x-coordinate is moving with it. So when the ant's x-coordinate is here, it's moved this far along the arc, right? And when the ant's x-coordinate is here, it's moved this far along the arc. Our work function is not a function of how far. We calculated work according to how far the ant traveled, but now the function tells us the work according to the x-coordinate of the ant, or the horizontal position of the ant. Does this make sense? So how far has the ant traveled at 0.559? How far? You said it's more than that. So when x reaches 0.559, how far is the ant gone?
Manipulation.
We would need arc length.
Okay, someone said arc length. Would we need the arc length function? Yeah, that's exactly what that is, right? The distance that the ant has walked when x is 0.559. That's our arc length function. Let's do it.
Oh, I was gonna ask something.
Sure.
Could you also cheat and use your accumulated work and then divide by your constant force?
Will that work? So, doesn't that assume something we don't want to assume?
That force is constant.
Yeah, well, force is constant, but x and s are not in a constant relationship, right? S changes at varying rates with respect to x because it's so wavy, right?
Right.
So that's not going to work.
All right. So avoid that. Thank you.
No problem. Right.
Does x equal the horizontal distance traveled by the ant?
Yep, it's the horizontal position of the ant. That's right. So now I want to know how far the ant has gone. What do I do? I want the arc length function, which is integral from Of what?
Square root of 1 plus ddt f of t squared.
Right, ds, right? I'm going to need my ds. So I'm going to need this thing right here. Hopefully I can copy and paste it. Good. So copy, paste, dt. Okay, and let's make this one red. Oh, no. Graph it. Where do we want to graph that? I want to graph that with the work. I want to graph that with the, let's graph it over here with the actual path. Okay, so x greater than 0. Here's the arc length function. How far? How can I find out how far has the ant walked at 0.559? When its x coordinate is 0.559.
Sub 0.559 into the x.
Yeah, I'm just going to type s of, use our function notation, right? 0.559. So when the x coordinate of the ant has reached 0.559, right there, right there, the distance traveled by the ant so along the blue path is like 1.58, like about 3 times as much as, or almost 3 times as much as its x coordinate, right? Because it has to go down and then up. So at this point, horizontal position 0.559, the ant has traveled this far, and the accomplished work is, according to our work function, 0.0475 joules. Okay, does that make sense before we add a layer of complication to this? I'm going to add one more layer of complication. Does it make sense?
Sure.
Yeah. Okay, so now the next situation is I want to have a variable force. So rather than the force staying constant at 0.03, this seed is gonna gain some dust, it's gonna gain some stuff as the ant pushes, and it's gonna require more force by the ant to push it. And so the new force function is gonna be, and I know the time, do not fret, I know the time, we're gonna just press on here, don't worry about the quiz, worry about the math for now. So then I'm going to have a new force function, and that's going to be 0.03. Oh, so this one, I'm going to use s as my dummy variable. So remember that this is a function of how far the ant has walked. So now, this is a different situation. The amount of force required by the ant is going up as the ant keeps pushing the seed. So now let's define the rate function separately for this. So what is the rate of change? What is the rate of change of this will be R2. What's the rate of change of work? So this is the rate of change of work. Force. And so what force do we have now?
Constant force 0.03.
Right. Okay, so I have this. So now my rate of change is going to be according to this force, F2. F2 of what? Here's the tricky part. So F2 of what?
S.
Right, so this is based on how far the ant has walked, not the x coordinate. But I want to write my rate function in terms of x. So what do I put here?
Square root 1 plus f prime squared dx.
Okay, but that's the rate of change of arc length. I want the arc length.
You would need to do the accumulation of it.
Right, and I've already done that. What should I type in here?
S.
S.
Parentheses AX.
Okay? Does this make sense? So the rate of change with respect to x is going to be the force, and that force is according to s, and s is an accumulation function itself, this one that we defined here.
Don't we need to pick a value for a, though?
Yes, we do. Thank you. So we're going to pick 0. Yeah, very good. Okay, but this is still force with respect to arc length, even though it's written in terms of x. So that this force, this is written in terms of x, but it's still force with respect to arc length. So we're not done yet. What are we going to need? We need to fully transfer this force to x to get truly a function of x and not. So this is written in terms of x, but it's still force per arc length, or force with respect to arc length. So I need to truly get this as force with respect to our x coordinate. So what else do I need?
ds.
Right. Well, this is the rate of change. So this is the rate of change. So I need that same transformation that I had before, right? So we took the force, and we transformed it from along the arc to x coordinate. So I need to do that again here. I've got the force in terms of s. I need to transform it to x coordinate, which is still this thing. But this is x. We're not in the integral here. Shoot. This is the rate of change now for this new variable force function. We had to write the force. It's a function of s, so that's what this force function is expecting, the s, which was our accumulation of arc length, according to this open form accumulation function, written in terms of x, but then we need to transform that f into, with respect to x. Okay, so a hush fell over the crowd. Does this make sense? So let's graph it quick. See what it looks like. So what about this? How's this one going to compare to the previous one? So how is our new work function going to, how will it compare to this one here? What do you think?
It would be higher.
She wants higher. The rest of you agree?
Yes.
Yeah.
Okay, and those who agree and say higher, why?
As you said, as the ant is pushing along this path, he would be like accumulating dust or something that would cause the force that he would apply to have to increase as well. So that means you're increasing the rate of change, which means an accumulation of such would be a higher value.
Oh, did you hear that? That was awesome. Great job. Yeah, so with a force increasing, you're going to have your accumulated work is going to be higher because you're working at a higher and higher force, so the amount of work required is going to be higher and higher. So, oh, please let this work. We got lots of functions going on here. So there I did the work. That's the rate of change of work. So 2. And I want to put that on the right side. We're almost done. We got to see this big conclusion here. And now notice how this work function was formed. You notice anything that's similar to what we saw earlier in class? Work is open form of rate, which is based on,
Closed form.
but open form of arc length. So what about graphing this? Oh, please work. It's working. So here was our original work at the constant force, was the purple one. Here's the new work at the variable increasing force. And so, like we said, that work is always going to be higher and increasing more. And why is it taking so long? Double layer of open form. We're writing the work function in open form, which is based on a rate function, which is based on arc length, which is an open form. Hallelujah, it worked. Does this make sense? Pretty cool stuff. So what I'm going to do is the quiz will be just an open quiz. It'll just be open without a due date. Take it as soon as you can. That'll be available later today. But once I get the homework updated, I'll post the quiz, and you can like take it anytime this weekend. The quiz, okay? Any questions?
Yes. Could you? Why is it that the work function is always? Why is the blue function always higher?
Because the force now required is increasing from 0.03. It's always higher. As the ant walk, it keeps getting bigger and bigger from 0.03. So more work is going to be more force is going to require more work.
Oh, okay. Thank you.
Yeah.
Wait, so you said more force requires more work?
Work equals force times distance. Work equals force times distance. So if force is higher, work is higher.
Gotcha. Okay.
Other questions? Someone else have a question?
I wanted to ask, just to clarify, so the W subscript 2 of x, that function is basically when our force is increasing at a certain rate, which we've defined in the
This
S
one.
of a to x, right, the integral below as well. So that's like keeping in mind that the arc length, that the ant is walking on that. Does that make sense? Like on the path?
Yeah, the force is a function of how far the ant has walked. And how far the ant has walked is our arc length accumulation function.
I see. So in the first work, we basically just did, 0.03 is our force, and we did not necessarily look at it from the perspective that it's walking along the path.
No, it is walking along the path. It just stays constant, so we don't need it's not a function of s, because it's just constant.
So why did we do s plus 1 in our second force?
To do a new problem.
Oh, so they were just two. Okay, got it.
Two separate problems, right? The first problem is constant force. Second problem is increasing force.
Awesome, thank you.
You're welcome.
I think the reason why it's s plus 1 is because the ant is starting off at 0.03.
Yeah, so the work, so it's just that the force starts the same, but increases from there. Yeah.
I see. So that's just an increasing, basically, force, and that's why we have an increasing everything. Got it.
Increasing work. Yeah, sure.
I just got a little bit lost when you added. So I understand that for the second rate of change for work, you need to have the second force, which is the varying force. But then, why did you use the s of? Why did you add the square root of 1 plus?
Because this is still in terms of it's in terms of x, but it's still the force with respect to s. It's still this function, and we need our rate function to be with respect to x. So this is the transformation. This is like the ds transformation from arc length to the x coordinate, just like we did here. So this is the force in the direction of s. So this is the force with respect to x, or the rate of change. Yeah, force. So it's the same thing. This is the force along s. So we need to transform that to as a function of x. The same thing we did here.